Yes, Janil, go
Yeah,
on.
I'm just sharing my presentation. One second. Yeah, I hope the presentation should be available.
Yes, yes, go on.
Yeah, yeah. So, hello everyone. I'm Janil Patel, a fourth-year dual degree student from the Department of Electrical Engineering, and today we'll be discussing the paper titled "Fat Load: Exploiting Locality Amongst Contemporaneous Load Operations to Optimize Cache Accesses." So yeah, so this is the rough outline of this presentation. So I'll just skip to the introduction. So yeah, so historically, spatiotemporal locality, which means that spatial locality and temporal locality, both of them combined, of memory accesses, is used to design storage elements. So we also observe that in most modern out of order processors, there are um, there are various memory access operations existing at the same time in different stages of processing inside the processor. So these accesses which occur or which exist inside the processor at the same time are known as contemporaneous memory access operations, and the spatiotemporal access patterns between such contemporaneous memory access operations can be used for optimization. And this theme or this idea is not novel, and various methods have been proposed in the past, which include store bypassing. So in store bypassing, basically what happens is that if a load is younger to a particular store to a same address, then the load doesn't have to go all the way to memory to access the value. It can just yeah, it can just take this value from a store cache or a store queue somewhere in the processor, and yeah, and save on those long latency memory access memory access service times. Yeah, so other idea is store combining, where multiple stores to very close regions in the memory can be combined, and a combined store can be done so as to save on the memory access bandwidth, or yeah, so to optimize the memory access bandwidth basically. And yeah, the novel idea being proposed here is of fat loads. So yeah, so here here what we do is, so as I said, in modern processors there are hundreds of instructions and many load instructions as well, or many memory access instructions existing contemporaneously. And so locality among such contemporaneously processed load instructions can be exploited, and we can classify a particular dynamic load into a normal or a fat load. So I'll come to what fat loads are in with a motivating example after this slide. So what fat loads basically do in a nutshell is they bring in additional data in addition to the particular load instruction which is tagged as a fat load into contemporaneous load access registers, uh, which are a level of hierarchy below the L1 cache. So these CLARs help service the load instructions with much lesser latency than L1 caches. And yeah, so other contemporaneous loads could be serviced without accessing the L1 cache and directly from the CLAR registers. So yeah, so this is a motivating example that is given in the paper as well. So this is a code snippet from the A-star benchmark. So here we see that there are various memory referencing operations. So we have this waymap array, and this waymap array, so the elements are data structures of some kind, and we see that we need fields of those. We need different fields of those data structures for comparisons or for branch predictions and so on. So yeah, so we see that this here waymap of index 1 is reference, and we reference a particular field, the fill num of that particular data structure, and we also use the num field of that particular data structure. And soon after this code this block of code is executed, there's another block of code which updates this index one, which basically this is an index into this Waymap array, and basically tells which particular element of the array we want to use. So this index one is updated, and it is just decremented by one, and then we proceed in a similar fashion as this code block. So these code blocks are nearly almost entirely identical. It's just that the index value is changed, and we see that this Waymap index one and the Waymap index one, which is updated, both of them we expect them to be close in. We expect them to be nearby in L1 cache. So what we can do is, while servicing this particular load, which is Waymap index one of .fillNum, what we can do is we can bring in additional data from these indices as well, right? So we can bring in data from this index minus y offset minus one as well. So fillNum and num values, and we can bring in data parallelly rather than just one element at a time. So we can bring in data. So yeah, in a nutshell, basically we bring in data from various indices at the same time. So in the paper, they saw that around 4 of these indices were being serviced in parallel. So we bring in data as a fat load. So all of this data is brought in at the same time and stored in the contemporaneous load access register, so that servicing them becomes easier, and we don't have to reference the memory again and again and keep going back and forth from memory memory and into very nearby regions as well. So we can bring in all that data as a fat load column. Yeah. So this is a motivation for the approach they've proposed. Right. So let's jump to the details then. So before we get to how this data is brought into the CLAR, we look at a few hardware structures which help keep track of various contemporaneous accesses to a region and so on. So first we look at the contemporaneous region access count table. So CRAC is a table where an entry is a region access counter, which is basically used to count the number of contemporaneous accesses to a region, and it has as many entries as there are equivalent lines in the L1 cache. So what we do is we keep referencing L1 cache with our memory operation, and if two loads reference, or if two loads are to the same cache line. So if two loads are to the same cache line, then we can just see that these two loads are contemporaneous and spatiotemporal in that sense, and they can be the load can be tagged as a fat load, and additional data can be brought in to service those loads easily. So yeah, for a 32 KB L1 cache with 64 byte lines, the CRAC has 512 entries as such, and the region access counter is a simple 4-bit up counter.
So yeah, I have a question here. The notion of region is same as line?
The region, they've used the terminology kind of equivalent.
No, is there any difference, or region is actually line?
Yeah, so somewhere they've used, so they've referred to L1 as the entire region they're working on, and somewhere they're referring to line. So here, in this case, I'm referring to cache line in particular.
So you count the number of requests that are coming to the same cache line.
Correct. Yes. So we have a time interval on which we count these number of spatiotemporal contemporaneous accesses, and we store it in this count table.
Got it.
Yes, sir. Okay. So yeah, so let's see how this bookkeeping is done. So if a load sees a non-zero RAC value in the selected CRAC entry, then very logically the RAC is simply incremented by 1. And yeah, so this is the issued load. Let's say it accesses this particular cache line, so the region access counter for this cache line will be incremented by 1 if the region access counter was not initially 0. So something interesting happens if this region access counter is initially 0. So a load that basically sees a region access counter of 0 is the first load to access that particular cache line at a given, so here again that's a cache line only. So that particular cache line at a given point in the execution of the program, and this load becomes a potential candidate for a fat load. So a potential candidate for a fat load, meaning that it is the first one to access that particular cache line, and subsequent loads that keep accessing the same cache line while that in that particular time interval, right, where the contemporaneous loads to a region are counted. So all of these loads can be combined into one fat load and can be serviced accordingly. So yeah, so this load.
What do you mean by can be serviced accordingly?
Yeah, so all of the data corresponding to all of these loads can be brought in at once inside the CLAR register.
Okay.
Yes. Yeah, so here this issued load sees, so assume that this issued load sees a region access counter of 0. It increments the region access counter obviously, but this load is also tagged as a potential fat load candidate, and subsequent loads to the same cache line can be serviced as a fat load, meaning brought the data corresponding to that, all of those loads can be brought in into the CLAR register, and yeah, so that is the basic idea here. Okay, so yes, so next so this is all for, the CRAC table allows us to kind of see how many, allows us to identify what are potential fat load candidates, and for each candidate we have a counter value, which basically gives us a prediction for subsequent runs of the same, or for subsequent iterations of, or how many contemporaneous loads can be serviced for that particular fat load candidate. So yeah, so this brings us to something which is used at runtime, or which is used at runtime. So basically this is done in order to obtain a particular profiling of the code, and this contemporaneous load access prediction table is used at runtime to basically make predictions about the number of other contemporaneous loads for a particular fat load candidate. So here we see that an entry contains a predicted contemporaneous load count, which is the same as the RAC value we obtained in the dry run, so to speak. And the CLAP, the Contemporaneous Load Access Prediction Table, is accessed with a load program counter, and the selected contemporaneous load count value serves as a prediction for the number of contemporaneous loads to the accessed cache line. So
why is this important? Why you need a number of loads, the count?
Yeah, so this count can be so this count can be used to evict cache lines. Firstly, basically, if we have some load which has more potential, or more more potential for contemporaneous accesses, then we can evict an already existing CLAR bank with this particular load, so that we can expect more. Yeah.
No, but that is already taken care based on the eviction policy priority bits, right? If you access more and more, then it will be closer to the most recently used priority.
Mm-hmm.
So what are you getting? What's the utility of so-called this CLC value predicts the number of loads to access CL?
Yeah. So this is just kind of Yeah, again, according to the paper, so there's also this other counter we maintain inside the CL, the contemporaneous load access register, which basically gets how many contemporaneous loads are remaining to be serviced for that particular bank. And let's say that we have a new load entering, and we have the CLC value for that load being greater than that particular remainder of the contemporaneous loads of the potential fat load candidate already in the bank. We can just kind of invalidate those CLAR lines and bring in data corresponding to the new fat load candidate, right? Because yeah, it has.
Okay. Anyway, move on.
Okay. Yeah. So how is this table updated? So when a potential fat load candidate is at the end of its time interval, it accesses the CRAC entry corresponding to the load address and obtains the RAC value, and it then creates an entry in the contemporaneous load access prediction table corresponding to the load program counter, and it sets the contemporaneous load count accordingly to be the RAC value minus 1. Okay, so let's so this is the so now we move on to the contemporaneous load access register. So here these are
This is too much detail actually. This is overwhelming for a presentation. Just at a high level talk about the utility. No need to explain each and everything.
Oh, I'm sorry. Yeah, I'll take out this one.
It's the end of the semester. I have been
Yeah,
telling it from the very beginning. Anyway.
yeah, yeah. So yeah, so contemporaneous load access registers are banks of registers used to hold the data brought in by fat load, and each bank has metadata for the data stored in the bank. So here we have this PRC bit, which indicates how many potential contemporaneous loads are yet to be serviced. So this is what I mentioned earlier, and this helps to evict and replace data inside these banks. And we also have these virtual address of the store region and page table entry corresponding to the store region in order to check permissions for various for memory accesses. Okay. So next we move on to the Cmap table. So this is used to determine at decode time whether a load can be classified as a CLAR load, that is load from a CLAR bank, or it yeah. So CLAR bank, and which means that it can be deterministically serviced from the CLAR during the execute stage, and it has as many entries as the number of architectural registers. So what we have is we have a load instruction and we have a base register for that particular load instruction, and this base register is the index for the Cmap table, and the corresponding entry gives us the location of data corresponding to location of the data we want to access inside the CLAR bank. So yeah, it has every entry has a valid bit and the identity of the CLAR register which holds the data. Okay, so we move on to the overall operation. So first we have the fetch stage, and during the fetch stage, the program counter is used to access the CLAP table and get a contemporaneous load count that is used to potentially classify the load as a fat load. Uh, So now in the decode stage, the base register of a load is used to access the Cmap and corresponding and the corresponding the corresponding location in the CLAR corresponding location in the CLAR register which we obtain from the Cmap tells us where the load could be serviced from, and the load can be so in the affirmative case, or in the case which is useful to us, the load can be classified as a CLAR load and dispatched, and the and the PRC field of the corresponding CLAR bank is decremented, which means that one less So yeah, which means that one contemporaneous access has already been taken care of out of the CLC number that was uh, originally predicted. And if the yeah, so again, so here we take care of evictions as well. So if the contemporaneous load count value is greater than the smallest PRC value among all the different CLAR banks, and the load is not classified as a CLAR load, then it is classified as a fat load and dispatched, and this fat load will evict the data um, from the from the bank with the smallest PRC value. And a load that is not classified as either a CLAR load or a fat load is dispatched as a normal load. So now we move on to the execute stage of the pipeline. So here the CLAR load is executed as it's just a move from the corresponding CLAR register to the destination register, and a fat load after address calculation, it populates the virtual address in the destination CLAR bank, and the Cmap entry for the corresponding the Cmap entry for the corresponding base register is set to point to the corresponding CLAR register. So we need to ensure that the data we are bringing in from the fat load also has a representation in the Cmap, so that we use it in further cycles. And the return data is placed in the destination bank, and once it is placed in the destination bank, the data ready bit is set to 1, and a normal load proceeds as usual. So in the final stage, the loads are just issued to the corresponding memory regions, and the loads without the page table entries that I discussed earlier need to go through the data table lookup buffer in order to obtain necessary permissions for memory accesses, and then they can be issued to the memory region. Yeah, so this is the so this is the overall operation of this proposed methodology. Now we move on to evaluation. So regarding the service types of load, so we compare 4 different cases here. So here, we have a store queue. So this is just an out of order baseline out of order implementation with just a store queue. And here we have an optimal store buffer cache in addition to the store queue. We have the CLAR as usual, and we have the L1 cache. So we see that store queue, so a significant proportion of accesses to the CLARs happen in case where CLARs are actually available. So this is the rightmost bar in this for each benchmark, and we see that even the number of executed loads is reduced. So we see that this has a slightly lower number of loads which are executed, and this is because CLARs help in faster servicing loads, help to service loads faster, and this can help to reduce the this obviously can help to predict resolve branch risk predictions at an earlier stage, so that more wrong path instructions don't get executed. Okay, so next we see the reduction in L1 cache accesses. So here 100 minus the height of the bar is the percentage of loads that end up going to the L1 cache. So here we see that all of these optimal memory servicing hardware actually helps helps to reduce the number of L1 cache accesses, and we also see that these CLAR configurations actually they do contribute to reducing the overall number of L1 cache accesses in that sense. Okay. So next we see the relative energy expended for L1 accesses. So the base case is just a machine with a normal store queue, and having just the optimal store buffer cache, we are able to achieve some energy saving. However, the contemporaneous load access registers are able to achieve significant additional savings. So the energy savings that we get is as high as around 49% with respect to the baseline. And yeah, so this is primarily due to reduced L1 cache activity and reduced references and access to the L1 cache, and servicing it from the CLAR itself. Yeah, so I'll conclude with this slide. So this is a technique to reduce the number of L1 accesses. We exploit the locality of references among load instructions that exist inside the processing window or nearly at the same time. And many loads can be serviced at a lower latency from storage within the core, which is the CLAR register. And reduced latency for some loads results in earlier resolution of some mispredicted branches. Yeah, so yeah, this is the conclusion. So we may have any discussions of this.
Okay, any questions, anyone? As usual, no questions.
Biswa, I just have a query in general. This paper is a bit counterintuitive in regards to reducing number of L1 accesses, right? Because generally we try to design the L1 in such a way, we come up with such replacement policies that most of the accesses get hit at L1, and we actually don't mind L1 accesses, or probably we need more L1 hits or something of this sort. So
that is still there, right?
Yeah.
So yeah, Daniel, so probably
that goal is not affected.
But then probably maybe I'm not clear with the motivation in regards to why they are saying that they need to reduce the number of L1 accesses.
Energy. If you reduce the number of accesses, then that will reduce the energy, because L1 cache is a major contributor of dynamic energy.
Probably by reducing the associativity also we end up achieving good energy benefits, right?
That will affect performance, right? Misses will go up. Like it's debatable, like depending on the workload, but usually you don't go for a direct map, L1 cache. So
okay, and do people explore the possibility of having a banked L1 cache?
Yes.
Maybe another trade secret of corporate world, but yeah.
Yeah, I think
okay,
you got
thanks.
the answer.
Yeah.
Okay. There is nothing much. Then Virendra, you can stop the recording and then give me permission to share my screen.
Yeah. Thank you guys for listening.